how do you determine the age of a microbe that you've sampled? Do you carbon date them? Because I know carbon dating is more for fossilization, but for something that's living, is there an accurate way to determine how old it is?
There is not. We don't have a good way to do it. So we have to infer that from looking at the total amount of energy that's available to the system, knowing how much energy it takes to turn over the carbon biomass in a cell, and then estimating how old on average the whole population must be. But carbon dating is something that we use frequently. If you work in very old systems, carbon, it turns out, is often very young. It has a half-life of only 5,000 years. So a lot of the places that I work in, it's too old to do carbon dating. You have to go to other radionuclides, other things that decay more slowly, because there's a whole raft. It's not just carbon. There's lots and lots of elements that have a very regular radioactive decay. So once you've gotten older than carbon, you can move on to the next thing. Okay.
And how, with the samples that you've collected, approximately like how old are they, if that's a fair question to ask?
How old are the microbes or the sediments or?
The microbes, the microbes.
I don't know.
Oh, okay.
The age thing is it's an inference based on what is available to this community in saying, I mean, that measurement, like the total energy that's available to them, is a pretty solid measurement, because we can see through the layers, we can measure the sedimentation rate of marine sediments pretty well, knowing the radioactive decay of various different radionuclides. And then from that, we can say, this is the rate at which they're using a particular chemical. And we know just how much energy is inherently available in the chemicals. So then we can say, they have this much energy available. And it turns out it's enough energy to make a new cell next millennium.
Okay. Oh, that's
so from that's how we infer that the cells are really old, just because they don't have enough energy to be young. But it's a guess. We can't measure it directly.
And do these cells, are they trying to replicate, or are they trying to just maintain their function, structure?
Well, if you're in a starvation situation, making a new daughter cell is like making competition for yourself. So there's probably some reasons not to do a lot of cell divisions in these situations. And they're probably just mostly at a maintenance energy, just replacing broken parts.
And do you think, like this maintenance of parts, do you think that these techniques can be applied to cultured cells? For example, cells that aren't prokaryotic, found in extreme environments, can they be applied to human stem cells or other cells that aren't in that lineage?
Sort of to keep them in stasis? I don't know. I think that would be really interesting. I mean, I think that one thing that we need to learn more about is the mechanisms by which, like how they manage to do this, how they stay in stasis for so long. We have a couple of ideas that may or may not be true, but they're just things that have popped out of the data. And one is that they seem to have a lot of this osmolyte called trehalose. And so it could be that sometimes the cells are sort of pickled in this osmolyte trehalose, and that preserves them. But we already do preservation techniques that are similar to that with cells that we maintain. So if you have a growing culture in lab and you put a cell stock in the minus 80 degrees Celsius freezer, you put it in glycerol first. And so it's sort of a similar function.
And then there's also certain other, like for example, spore forming microbes that once they form the spore, they can kind of go into stasis and stay in that form for extended period of time as well.
But there's an interesting thing about spores, and this is pointed out by Rick Morita in the 90s, that a spore is really not active. They can't do anything to maintain themselves. So they're a great way to hunker down for a year. But if you need to hunker down for 1,000 years, then you need to be active. You can't be dormant, because you have to be working to maintain yourself.
Okay.
Spores are actually not a great super long-term strategy.
Yeah. Okay. That's interesting to learn. And then, so when these microbes,
Just a minute, Robbie. Hey,
go ahead.
Where is it? Basically, sorry.
I was going to ask, so when you trace these, the lineage back, are there other, let me just think about how to ask this. Are they, do certain microbacteria share the same characteristics, or have they all evolved different ways of surviving these harsh conditions? For example, you said that certain prokaryotes, they're in a starvation mode, so they do everything they can to replace old parts. But have you seen microbes that have been able to survive comfortably in these harsh environments?
Well, comfort is an interesting word. I think they're all pretty comfortable. I mean, it's a good gig. They've got enough. They can live for a while. You know, they don't do much, but it's kind of like I don't know if you ever watched The Big Lebowski, but I think sort of the point of The Big Lebowski is that the dude just wants to abide. He doesn't want to like do anything. He's not going to like make an impact on the world. So, you know, they're kind of like that. You know, you can find happiness in nothing.
Just chill. Yeah.
So, but I mean, we don't have enough. We don't see any evidence that there's some go-getters around who are like really striving and growing and stuff. We're looking over long enough timescales that if somebody did sort of get their motor running and started really growing, then we just see them take over. So you do see parts. If you look down sediment columns in different parts of the ocean, there will be sort of layers of stuff that cause a bloom to happen. So you'll see that you get some go-getters when there's food.
Mm-hmm. And do you think that these cells, if you starve them of zero energy, do you think they'll eventually die? Like,
yeah.
Have you tested that? Like, that's a cruel thing to do to a prokaryote, but have you done that experiment?
No, I mean, I can say just from first principles, if there's zero energy available for a long enough period of time, every living thing will die. Any living thing will die. Just like they're definitely killable for sure. But you know, I don't tend to study them alive anyway. So.
Mm-hmm. And the last question that I wanted to ask was, with what you've studied and the research that you've done, do you think there's evidence to suggest that antimicrobial life can grow on other planets or in places that we haven't really explored yet?
You said antimicrobial life?
Or sorry.
You're thinking about medicine.
I'm so sorry. Microbial life on other planets.
Yeah, absolutely. I mean, I don't see any reason why there shouldn't be microbes underneath the ice caps of Europa or even on Titan. They could still be in the subsurface of Mars as well. So, you know, there's really nowhere we go on Earth that we don't find some microbe living. And given their ubiquity on Earth, it just makes sense that they've got to be on some other planetary body. So we don't have evidence for it. That we do not have. But I absolutely think that they're out there somewhere.